Hello guys, welcome back to my YouTube channel. This is MJ School of Mining and Geology, where we delve into the fascinating world of the earth sciences. Today, join us on an exploration of an isochron dating, a powerful technique that unveils the secrets of our planet's past. Isochron dating, it's a method used by geologists to determine the ages of rocks and minerals. It's, it is based on the principles of radioactive decay and isotopic ratios. Please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. So the isochron is just a line on the ratio of radiogenic isotope diagram connecting points representing an equal time, or what we call the cogenetic samples of minerals. Okay, but we're gonna talk more about that. Okay, so it requires 3 or more cogenetic samples with a range of ratio of, for example, because today I'm gonna explain this using the RBSR or the rubidium strontium system. Okay, 3 cogenetic rocks derived from the single source, okay, by partial melting or fractional crystallization. Okay, so cogenetic rocks means rocks that are derived from the same parental magma. So 3 coexisting minerals with different ratios of rubidium and strontium, or potassium and calcium ratios in a single rock. Okay, so it means coexisting minerals means minerals that occur together in the same rock. So for rocks to be cogenetic implies that they are derived from the same parental magma as explained. So the parental magma would have had a single strontium 87 against the or the ratio of strontium 87 and strontium 86 isotope value. That is the initial isotope value. They must have the initial isotope value. Okay, but I'm gonna explain to you in a few what do we mean when we say they must have strontium, or what you call the isotope values, or the initial isotope ratios. Therefore, all the samples derived from the same parental magma should all have the same initial strontium 87 over strontium 86 isotope ratio. So because they were derived from the same parental magma. If they don't have initial isotope value, it implies that they were derived from a different parental magma. So keep that in mind. So like I said, today we're going to be using the system RBSR, okay, or the rubidium strontium ratio, the system. So the crust and mantle have varying in strontium isotopic composition, and this has happened over time. So we must understand the evolution of the RBSR system over time. So how the system evolved depend on how rubidium and strontium partitioned into different reservoirs during the early Earth evolution and the subsequently afterwards. Okay, we will investigate using a simplified single stage model for Earth evolution, not entirely realistic, but sufficiently realistic to understand this system. Okay, so strontium 87 is stable and therefore non-radiogenic. Okay, non-radiogenic. It does not when we say something it's non-radiogenic, we mean it does not decay. Okay, does not give us the daughter. Okay, so but rubidium 87, it's radioactive. It means it decays. So its abundance decreases with time as it decays to strontium 87. Okay, so when we say something is a radiogenic isotope, we mean it's a daughter isotope. Okay, it's a daughter isotope. So when rubidium-87 it decays, it gives us strontium-87, where in the strontium-87 it's non-radiogenic. Okay, then now strontium-87 it's a radiogenic. Strontium-87 is a radiogenic, a product of rubidium-87. Okay. So its abundance increases with time as it forms from the decay of, it means decay of a rubidium-87. It means the more rubidium it decays, it will produce more of the strontium-87. So strontium-87, it will increase with time, but rubidium-87, it will decrease with time. So like I said, rubidium-87, it's radiogenic. We mean it's a daughter isotope, but now it will never decay further. Okay, so now higher ratio of strontium-87 over strontium-86 means more radiogenic strontium has been produced. But if we have got lower ratio, it means less radiogenic strontium has been produced, because now as you can see that from this ratio, okay, so this, it's just like when we say 87 SR and then 86 SR, just like that, and then now and then we've got SR like that. So these, they are directly proportional. So it means now when they are directly proportional, that is to say, the more when we have got the more of these, okay, the more of this ratio, it means more of radiogenic strontium has been produced because of a direct proportionality. Okay, so we're going to be using these ratios. Okay, so now constructing this isochron, rubidium strontium is useful for rocks and minerals with abundant rubidium. Okay, and thus K-rich rocks and minerals, normally micas such as biotite and muscovite, and feldspars, clay minerals, also sphalerite, okay, which accommodates rubidium but not strontium. So this is just to give you a picture of the rocks and the minerals that they've got high amount of rubidium, okay, and strontium. So we often construct an isochron from a suite of cogenetic rocks, especially 3, at least minimum of 3 samples. Okay, a single rock or what you call a whole rock mineral isochron, and also a number of minerals from a sample mineral isochron. Okay, assumption is all rocks are cogenetic and have remained a closed system since formation. Okay, so when we say closed system, it means the production of the daughter isotopes will still equal to the rate of production of the daughter isotope will equal to the rate of production of the parent isotopes. Okay, so and then when we say the rocks are cogenetic, it means that they were derived from the same parental magma. This is the assumption we need to keep in mind for especially for this. Okay, so what can we learn from this isochron? Okay, after each period, the rubidium-87 in each rock decays to strontium-87, producing a new line. Okay, because now we say rubidium-87 is a radioactive. It's the one that decays into a new thing, which is strontium-87, which is a radiogenic. Okay, which is a radiogenic. And then yes, so this line is still linear, but is steeper than the previous line. Okay, I'm gonna mention that to you, that especially the importance of what you call the slope, and not only the slope but also the initial ratio. But I'm going to mention that in a few, that these things, they are very important, especially the slope. Okay, so yeah, but in a few, I'm going to explain all that to you. So, and then we can use this to tell us two important pieces of information: the age of the rock and the initial strontium-87 over strontium-86 isotope ratios. Thus, the isochron method is usually used for determination of the initial strontium-87 and 86 ratio and the age of the rock. Okay, so which is why we say this is the powerful technique. This is the powerful technique for the determination of the age. Okay, so this is because as I mentioned that I will discuss that in a few with you guys, that the slope, or the line slope, okay, will always correspond to the age of the samples. Okay, and then but now the y-intercept of that particular graph will represent the initial isotopic ratio. So the most important thing will be the y-intercept and what we call the line slope. Okay, so because the line slope will always correspond to the age of the samples. Okay, so now this is the graph we've mentioned. So I want to bring this to attention, that from mathematics, we've especially line graph, we've learned about this, and then we've learned that this is what you call a slope, the slope of the graph, and then this is what you call the y-intercept. Okay, this is exactly what we have learned. So now this formula over here, it has the same analogy with this graph. Okay, wherein now let me show you. I can say this is our y, and then this is our c, and then this is our m, this is our x. Can you now see? It means, okay, now this ratio here, strontium-87 over strontium-86, it's the initial ratio. It's what you call the initial ratio. It's what you call the initial ratio. But now it's the y-intercept, which is why it touches the graph here. Okay, it touches the graph here. Sorry about that. It's the y-intercept over here. That's this initial ratio. It is the y-intercept of the graph. It's the initial ratio. And then now the slope of this line, it's given by m. Okay, it's given by m, and it's strontium-87 over strontium-86. Okay, but now this value is measured. Okay, and this value is measured. So we measure this using what you call some analytical equipment. Okay, and then yes, so I want to bring this to attention. Now, as I've mentioned, that now that this slope will always correspond to the age of the sample. This slope will always correspond to the age of the sample. But now the y-intercept will represent the initial isotope ratios. It will always correspond to what you call initial isotopes. Okay, so it means now no matter how much time has passed, okay, because initially we were here, okay, and this graph or this line evolved, okay, towards that. And then if it means also over time it can also come somewhere here, then over time it can go here. Okay, so now, but no matter how time has passed, the isochron method allows to determine the initial isotopic ratio reliably. Okay? Because we would always have the initial isotopic ratio. Okay? Now, it means now by analyzing the slope and the y-intercept of the straight line through a series of cogenetic samples, we will always use this or the isochron method will always be a powerful technique for determining the ages of rocks and minerals. Okay, now the rubidium, strontium, useful for rocks and minerals. Okay, then I've mentioned this, and then but now note that rubidium and strontium are very mobile during metamorphism and alteration. So this technique is suspect in altered rocks. So you must be aware. You must be aware that it may not work for every rocks. Okay, might not work for every rocks. I don't know what's happening. It doesn't want to erase. Yes, so let me now take you through this process. Okay, so I've divided this process into 5 stages so that now you can follow what is really happening. Okay, so the rocks were assumed to be derived from the same parental magma. From the same parental magma, it means they are core-genetic. Okay, so we start, remember we said for us to plot this we need 3 cogenetic samples, okay, and minerals. Now we've got rock A, B, C, so we are fine. So we start by plotting 3 rocks with different rubidium content at time 0. We've plotted them, we are fine with that. Okay, so after we done plotting that, what do we do? At time t1, some arbitrary time after time t0, some of the rubidium 87, because this is radioactive, has decayed to strontium 87, because now this one it's a radiogenic, it's the daughter isotope. Okay, so the more rubidium in the rock, the more we're gonna have the daughter. Okay, because we said the rubidium 87, it will decrease with over time, but the strontium 87 will increase with time, because it's like the reactant and the product. So rubidium 87 is just the reactant, and then strontium 87 is just the product. So we know the more we use up our reactant, the more we're gonna produce more of our products. Okay, so I hope you understand. Now moving to stage 3, if a straight line is fitted to these evolved points, okay, because this point were here, then they evolved with time. So if we now have a straight line, can now see that here we don't have any straight line, but now stage 3 we have a straight line now. Okay, now we fit all these points. So if a straight line is fitted to these evolved points at time t1, they also fall on the straight line that has the same initial strontium 87 and strontium 86 ratio at time t0. So no matter the evolution, but if we connect all these samples, they will also all of them, they would have the same initial strontium 87 over 86 ratio. Now, similarly, after time T2, okay, the rubidium 87 in 3 rocks will again have decayed to strontium 87, but a straight line through the points will give the same strontium 87 over strontium 86 ratio as time T0. Okay. Notice now that no matter how much time has passed, a straight line, this is most important, through a series of cogenetic samples will always give us the initial strontium 87 ratio. That is the same y-intercept, which is why I brought to your attention that the y-intercept will represent the initial isotopic ratio. Okay, so the isochron diagrams a straight line through a series of cogenetic rocks. Okay, the rocks formed at the same time from the same parental magma. Samples will always yield the initial ratio, okay, of parent and daughter isotopes. No matter how much time has passed, they will always, these cogenetic rocks will always yield the initial ratio of both parental and the daughter isotopes. That is to say, can you now see we have got they would always have the same initial ratio. Okay, they will always have the same initial ratio. I hope it makes sense. This is because the mathematical relationship between the isotopic ratios and this is because of the mathematical relationship between the isotopic ratios and the age of the samples. So the principle behind isochron dating is that if all samples in the data set were formed at the same time from the same parental material, that is to say they are cogenetic, but with varying initial isotopic composition, plotting the isotopic ratios of parental and daughter isotopes against each other will result in a straight line. Okay, will result in a straight line, and that straight line, it will be, irrespective of the time. Okay, the straight line will always start from the time 0, where we have initial strontium 87 and strontium 86 initial ratio. This line slope will correspond to the age of the samples, and its y-intercept will represent the initial isotopic ratio. So it means no matter how much time has passed, the isochron method allows us to determine the initial isotopic ratio reliably by analyzing the slope and the y-intercept of the straight line through a series of cogenetic rocks. Okay. This makes isochron dating a powerful tool for determining the ages of rocks and minerals. Here's why this happens. Okay. That is to say, why the line slope corresponds to the age of the samples and the y-intercept representing the initial isotopic ratio. Okay, now the constant decay rate. The parent isotope decays into the daughter isotope at a constant rate over time. This means that for any given sample, the ratio of parent to daughter isotope changes predictably with time, because we know the parent will keep on decreasing while the daughter will keep on increasing. Okay, provided we are in a closed system. Okay, now cogenetic samples. Since all the samples in the data set are cogenetic, they all started with the same initial isotopic ratio. However, they may have experienced different degrees of radioactive decay, leading to variations in their current isotopic ratios. So now, when plotting the isotopic ratios of parent and daughter isotopes against each other for all samples, the variations caused by radioactive decay cancel out, leaving only the initial isotopic ratios as the y-intercept of the resulting straight line. Okay, so I hope this lesson was helpful. If you don't understand, you're more than welcome to ask me, and then I'll be pleased to help you guys. But above all, do not forget to like, share, comment, and subscribe to our content so that we keep producing this kind of a content. Until next time, Cheers.